Hello, fellow fans of 3 Blue 1 Brown. I'm Krishna Sampath, and in this video, we're going to be talking about exotic Brachistochrones. Not any Brachistochrones, but some exotic ones. So to say, all right, let's set the stage here. So let's say we have 2 points A to B, and a bead like this needs to go from A to B solely acting under gravity. If it takes the straight line, it certainly will be the shortest path, but will it also be the quickest path? That's the question that scientists and mathematicians have asked for over 3 centuries now. So there is this inherent trade-off here between gaining speed by falling down vertically versus getting closer to the target. So is there an optimal path that this bead can take in going from A to B? This problem has a celebrated history for almost 400 years, starting with Galileo, Bernoulli, and then who's who of the mathematical and scientific community from back then. And it has continued to fascinate the community since then, and people have solved variations of this, and we are no exceptions. Um, my wife and I worked on it for the last 5 years or so, and then we were able to solve the variation of this, which is what would be the brachistochrone of eccentric cylinders or off-centered cylinders, which is what we'll be talking about today. So we can get an off-centered cylinder by just varying the density distribution within the cylinder, as indicated as an example on the top left picture here. With a system like that, we set up the dynamics of it similar to how we would for the bead, but we also consider as additional aspects such as the rotational dynamics and the fact that this is an off-centered cylinder. So we start with physics of the problem, which is always the foundation, which is basically an energy balance between the rotational and kinetic transmissional energy with the potential energy. And then we go to calculus of variations for minimizing the transit time. And then we invoke arc length formulation for capturing the curvature of the path precisely. And finally set this all up using numerical methods and then obtaining our solutions. So before we get into the actual solution of the brachistochrone, let's look at what this off-centered cylinder would do in some of the standard curves. So let's begin with an ellipse. We see that it's fairly short and it takes about a non-dimensional time of about 5.9 seconds, 5.9 units. And if we were to let the cylinder roll through a circle, it takes a time of about 5.44. Although it's visually a longer path, it takes advantage of the fact that it is falling a deeper height or depth and thereby gaining more speed to reach its destination. And then we have the cycloid, which by the way is the solution for a uniform cylinder where the center of mass is its center of cylinder as well. You can see that it's kind of a trade-off between ellipse and circle in this case, so to speak, and it has a time of about 5.2 units. But if we actually want to see what is the brachistochrone of off-centered cylinders, it's rolling in front of our eyes right now. So because it's off-centered, it takes this nice, interesting bump along the way or dip along the way, and then reaches its destination, and it is actually reaching it in just under 5 time units. So it can actually be quicker than your uniform cylinder based on the path it is taking. Okay. So this was for the solution actually gets even more interesting when we let the center of mass of the cylinder vary and then redo these simulations. On the top left, you're looking how it would change if you were to move the center of mass in and out within the cylinder. And on the bottom right, we're looking what it would do to the path if we are changing the initial orientation of the cylinder. We get this wonderful family of brachistochrone paths for off-centered cylinders. So when we plot the dimensional less time over that entire parametric space that we just explored, which is the initial orientation in the angular direction and the radial direction, we get this beautiful spread of the transit times, and there is actually a global minimum for the orientation, which can give you the shortest path, shortest time between those 2 points. And in this case, it happens to be when the center of mass is 30 degrees below the horizontal line, and it is about 70% of its way along the radius. So with that, let me leave you all with this image of a skateboarder and an unsolved problem as to what should be the path that the skateboarder has to glide, which would give them the shortest time or the maximum speed by the time that they reach there. Thank you for watching.